So today we have like the new version of larkos. That would be now larkos 03. So what we can do immediately is we will actually see into the outputs, which we didn't even read before, but yeah. So okay, as we can see, because like the text is mainly just a debugging thing, not like I don't actually train the model to have text or like respond to your questions ideally, but we can see it predicts okay text, so like the text bridge is working and other stuff. But yeah, what can we see from the outputs actually? So here we are training with 128 neurons, I think. Yes, with 128 neurons, and we can see some things we can see immediately. We also have bigger input sizes, so those tensors are normally quite low, but you can see it fuses, our fusing mechanism works. We have learning rate, the loss the loss decreases over time. Obviously you can argue that the model just memorizes, but we have here so many systems to prevent just that, so memorizing, so to allow the model to actually learn. And we need to remember that we can't just train like a couple apertures, we need a bit more to like let all of the C backend do its things. We also have the memory, it fills the memory correctly with the clusters and embeddings. Yes, so we can see the text makes more sense. The emotional system is working correctly, though in realistical training we shouldn't use emotional and affective systems. They are just here mostly for testing purposes. We can see the loss is working okay, so auxiliary predictor loss and base. So yeah. As we already know, the tests obviously pass, most of the time, and they provide us with actual margins. We shall not look into them today, but yeah, what I wanted to focus on today is this. So the live preview, you can say. Not the live preview, but the actual architecture. Okay, so what we actually introduced in larkos 0.3 is the gut layer and so the graph-attentio. Basically, we didn't really use attention before, we just relied on cross-attention, and now we actually use an attention mechanism to allow the model to base context from them, and this also allows us to like better view the whole thing. So if I took this, and here we like have here we will have just output, right? Out. So here we have neurons. Oh, this might not work. Okay. Here we have neurons. Here we have LLM DIMs and inputs. And so this passes through the gut. This also will go down to weights. I can't draw if my life depended on it. Weights. Here we also have the whole reasoner, so here we use the whole like graph-attentio to combine it into out context and out transformers. So if we had here the decoding, So did the coding here. The coding here we would have graph-attentio plus transformers on the fusion things. So we basically changed the fusion mechanism a bit, so the graph-attentio more focuses now with the fusion things, and we just, so we don't have that static projections, we actually train those projections, you can say. Yeah, and here obviously we also have weights, and this also interacts with out, but yeah. So yeah, we have the GAT, the neuron graph reasoner, so the stuff we just talked about, which uses the C side, yeah, the C side, and we basically rebuild everything here. So we build the inputs here, we have the neurons, when we do the forward passes, etc, etc. But we still obviously use the fusion, just we change it a bit, so instead of the default free stream tokens, we have per-neuron tokens, so from the stuff that happens with the graph reasoner, neuron graph reasoner, as I said, the default band Q and band M, and the driver embedding, so the LLMs thing is, yeah, and that's mostly it. We also in the 0.2 version switch the Adam optimizer to Adam V and different also things, but now we should probably look into the architecture. So if I now okay, so it's quite big and it's quite laggy, but here's basically, you can see that they are like organized into different modules. So here we'll have input pipeline, here the C backend, here the side effects, and if we look into the start, so the input pipeline, we build the input tensor, we do encodings, and we send the input tensor firstly to the C side, and this is used by the neurons, which then the neurons are used by motivation system, imagination system, reflection system, and this is later used by the side effects, or our backend. So we do update motivations, we do the reflection, we do processing neurons, updating neurons, we do tanh with simd, we run reflections, we update imaginations, and yeah, we basically update the C side states. Here we also later pass more things into it, so when we already have predictions, okay, well, we'll get to that later. We also start with mini LM, so basically it's quite efficient for its size, and it's okay, I guess. We don't really need to create like learnable decoders in this, because I mean, it's supposed to be experimental architecture, not a whole working model, and that's why we also have the whole affective system after all in this. I doubt we would actually want this in a normal model, I mean, unless you want some I don't know, companion model. I don't know. This doesn't sound that good, to be honest. So yeah, after we project everything, we do the temporal stuff, we use the transformer encoder, we later pass it into the the embedding branch, so we run our embeddings, we do our cross-attention, as I said, and yeah, we later pass again the LLMs and cross-attention and other stuff into the context manager, and this context manager will later, okay, here we also, yeah, and from this, once we pass all of the here, we get to the fusion mechanism. So we use Distill GPT-2, as I said, text quality doesn't really matter here, and Distill GPT-2 is just lighter to run. Also, I am running this whole model on 12 gigabyte VRAM, so I can't really afford to. So I really need to like focus on the optimizations. Once we embed everything we get from here, yeah. Well, Fusion DIMMs isn't always 64. I don't know why I wrote it in the documentation like that, but the hash is 64. Okay, so yeah, we later use the band M and band Q, like we already sorted the code. We do the crossband mixing, we run some math on it, we get fused cook row, so the of size Fusion DIMM. We recenter fused cook each epoch, and we later construct the default weights like I showed on the drawing. I'm just not good at drawing. Also, as said, current system state, neuron predictions. We later blend all of this stuff, so importance with the memory, project X, layer norm. Okay, we'll also get into this, so the two modules, so the AML inner loop. So we just clone the model, share throws and a mini-LM encoder. We only refresh chainable parameters, and we avoid the 22 million param copy. This is just for the mini-LM, because like this used to, in the larkos 0.1 version, to use a lot of resources. We later run inner SSD, so like a small AML inner loop, and okay. Here we also, during training, we also freeze weights to like work with the bigger epoch sizes. So we derive, we cage, we use the so the graph-attentio still works with the fusions, but we just freeze things at cage. Now, if we go to the loss and optimizations, we have that loss equals, here we just compute loss, it's not really interesting. We get to the grad balancing, so our gradients aren't too big. And here we have the ADM so what I already talked about. We do cos, and it's just default stuff. Let's get to something more interesting. Okay. Here we have the C side again, so the specialization system enter here, what I forgot to say. And here we have the whole self-identity, so identity system and memory, which enter through here. And we also have decision paths, which are very important. This is basically like it allows the model to run different paths of decisions, but this is basically from the larkos architecture, so I won't really get in detail here. Okay, here we have the fusion transformer, we have the models and graphs as said, because we now use graph-attentio. We have this, so Q, M. We project as before, and we have the sequence, we do our fusion, we do our transformer stuff until we get to the whole fused transformer. Here it's, here we have the neuron graph reasoner, so like the more interesting stuff. So we build the graph inputs with certain sizes. We construct our gate layers, we do leaky relu, and we normalize after that, and we pass this into the transformer head, so this interacts with this. And this is the last stuff, so the dropout probes, so when we do dropout, when we do what, for exploring from dropout, so the other average stuff. That would be pretty much all when it comes to the whole architecture. Allows you to get started, but you should actually read the training.py file for what actually happens here. So this, so read the comments actually. That would be pretty much it.